Hello students, I Neha Yadav, Assistant Professor in ABES Engineering College, is going to teach the seventh topic of Unit 4 of Discrete Structure and Theory of Logic. The topic is Group Homomorphism, Ring and Field. What is group homomorphism? A mapping F from a group G star to a group G dash O is called group homomorphism from G to G dash if the given condition is satisfied. The condition says that if we apply the operation given in the first group between two elements, considered elements, and if we give this as an input to the mapping F or a function F, then it should satisfy this condition. If we give the first element to the function and then perform the operation by giving input of second element to the function, if this condition is satisfied, then these two group G and G dash are said to be homomorphic. For example, here in the example, two groups are given. The first group is R plus. So here the first group G is the set of real number and the operator is addition. The second group G dash is set of non-zero real number and the star here is the multiplication. And the function given is fx is given as 2 to the power x. So here we have to check whether these two groups are homomorphic group or not. So let us consider any two element which belongs to the set of first group. So here the first group have the set of real number. So consider any two real number. Let it be x1 and x2 be any two real number. If x1 and x2 are two real number, then we will check for this condition. If this condition satisfies, then I can say that G and G dash are two homomorphic groups. So I will check for the condition. Here the function given is 2 to the power x. So 2 to the power x. In place of x, I will just write two numbers, two considered numbers, and apply the operation given in the first group. So the operation given is addition. And then here I will split these two numbers. I will give these number as input to the function first and then apply the operation. So here it will be, so we will check whether this condition satisfies or not. So we know that we can write this as, sorry, this is x2, this as this. So RHS is equal to LHS, hence the condition of homomorphism is satisfied. So these two group, a group with real number and addition and a group with non-zero real number with multiplication are two homomorphic group. Consider another example. Here the question is given, show that the multiplicative group, the group is multiplicative, it means the operation is multiplication operation. So the first group is G is given, the set is 1 minus 1 and the operation is multiplication. So I can use star for multiplication. And the second group is, here the mapping is group. So here the first group is not this is G dash and first group here is this. And the function given is this. So we have to take any two element which belongs to the first group. For example, I will take x1 and x2. So for applying this function, there are four cases. X1 can be the first case will be both x1 and x2 will be even. The second case will be both x1 and x2 are odd. The third case will be x1 is even and x2 is odd. And the fourth case will be x1 is odd and x2 is even. So we will solve this question using these cases. The first case is case 1, where the integer considered are both even. X1 is even and x2 is even. So if we check for the condition is f x1 plus x2 should be equals to f x1 star f x2. So here the question given is, the function given is, I am writing the function here, fx is equal to 1 if the value of x is even and fx is equal to -1 if x is odd. So here we know that x1 and x2 both are even, then the summation of x1 and x2 will also be even. So f of even will be, we have to check f of even will be the x1 is even. So f of even into f of even, and the function is given. If x, the value of x or the input to the function is even, we will get the output as 1. So here it will be 1 into 1. So RHS is equal to LHS. So first case is satisfied. Case 2 will be x1 is even, sorry, consider the case 2 as x1 and x2 both odd. Both odd. So here, if we apply even plus odd, yeah, here we are considering both as odd. So if we add two odd numbers, we have to check this condition. This is multiplication. So two odd numbers, let it be 3 and 1, it will always give you even. So two odd number will always give you even. This is the odd number into odd number. So now we will give the value to this function. F of even is, when x is even, the f will give you 1. And when f is odd, the x is odd, then function will give you -1. Here also we will get 1 is equal to 1. Hence RHS is equal to LHS. The next case is case 4. Case 4, when x1 is odd and x2 is even. This is case 3, not 4. So when x1 is odd, so we have to put these value in the function. Odd plus even, f odd into f even. So let's see. F odd plus even, what we will get when we add one odd number and one even number. Let it be 2 and 1. We will always get odd. And f odd, we know that it is -1, and f even is 1. F odd is -1, and this is also -1. Hence LHS is equal to RHS. Case 3 is also satisfied. Similarly, case 4, where we will take x1 is even and x2 is odd. Here also we will check for the condition of homomorphism. F even plus odd is equal to f even into f odd. So here also we will get f even plus odd will always give us odd. So -1 is equal to -1 into 1. Here also we will got -1 is equal to minus. Hence LHS is equal to RHS. So we can see that all the four cases are satisfying the condition of homomorphism. So the two group Z plus and G, which is 1 -1 with multiplication, satisfies the condition for group homomorphism. So these two groups are homomorphic group. Next is ring. What is a ring? The structure R is a non-empty set. First operator and second operator. These two operators are binary operators. The structure this consisting of non-empty set R and two binary operators denoted by plus and star is said to be a ring if these three conditions are satisfied. For a structure to be a ring, these three conditions should be satisfied. The first condition is the set with addition or the set with first operator should be a abelian group. And we already seen what is a abelian group in the previous lecture of this unit. The second condition is the set should be a semi-group with the second operator. So what is a semi-group? We have already checked what is a semi-group in the previous lecture. The third condition is any three element which belongs to the set should satisfy the distributive property. It can be a left distributive property or a right distributive property. If this structure satisfies all these three properties, which is the set with first operator should be abelian, the set with second operator should be semigroup, and any three element of this set should satisfy the distributive property. If these three properties are satisfied, then the structure is said to be a ring. For example, let us consider the structure set with which is a set of integer. The first operator is addition and the second operation is multiplication. Here the star is multiplication. We have to check whether this structure is a ring or not. So we have to check the first condition. The set with first operator is abelian or not. The second condition, the set with second operator is semigroup or not. And then the distributive property. If these three properties will satisfy, then this structure will be a ring. So for abelian, we have to check for closure property. What is closure property? Closure property says that if we apply this operator, means addition operation between any two elements of this set, between any two integers, then the result should belongs to this particular set. So we know that if we apply addition operation between any two integer, we will always get an integer. So in this case, the closure property is always satisfies. Next property is semigroup, or the property is associative property. So if we consider any three integers, for example 1 plus 2 plus 3, and we change the operations, this example is also discussed previously in the previous lectures of this unit, so you can refer from that lecture also. If we change the associations, for example I add 1 and 2 first and then I will add 3 to the result, or I can add 2 and 3 first and then I will add 1 to the result, we will always get equal value. So associative properties is satisfied and hence this is a semigroup. Now the third property for abelian is we have to check for identity element, or the structure should be monoid. So identity elements, and we know that for plus the identity element is always 0 and 0 always belongs to the set of integers. So identity element exists. Next we have to check for inverse. Next we have to check for inverse. So here, how to find the inverse? Consider any integer, for example a, apply the operation, and we have to apply the operation with this inverse value so that we can get the identity element. So we know that the inverse will always be, I is always be minus a. So minus a is also a integer. So here inverse of each element of the set integer will also exist. And the next property is the commutative property. So we know that addition is a commutative operator. If we add a to b or b to a, it will always be equal. So the fifth property, which is commutative property, also satisfied. So Z plus is a abelian group. Similarly, we will check for Z multiplication, whether it is a semigroup or not. So we will check whether whether Z multiplication is a semigroup or not. For checking Z multiplication is a semigroup or not, we just need to check two properties, closure and associative. So we know that closure property, if we multiply any two integer, for example 3 and 300, we will get 900, which is an integer. We will multiply any two integer, we will always get a integer, hence closure property is satisfied. And associative, if we apply 1 into 2 into 3 and we change the operation, it will not affect the result. It will always be 6 is equal to 6. So both properties are satisfied. So this is a semigroup. This is abelian, this is semigroup. Now we will check for distributive properties. Distributive property says that a plus b multiplication c should be a plus b. In between we will apply multiplication a plus c. Take a, b, the value of a, b, c, any three integer value, let it be 1, 2, 3. So 1 plus 2 multiplication 1 plus 3. 1 plus 6 Here 1 plus 2 is 2, multiply 3. 3 plus 1 is here 1 plus 2 and then multiplication. So this is 1 plus 2 is 3 and this is 4. Here it is 1. So here the distributive property is not satisfied. We can see that it is 7 and this is 12, which are not equal. So here the first condition was satisfied, second condition was satisfied, but the last condition was not satisfied. So this integer with addition and multiplication is not a ring. Coming to the definition of field, what is a field? A field is a ring which satisfies the following properties. The first property is same as the property of ring. The set with first operation should be abelian. The second property is the set with second operation also be a abelian group. And the third property is distributive property. So the second property is different for ring and field. The first and third properties are same. The first property is the set with first operator should be an abelian group. The third property is distributive property. The second property for ring was the set with second operator should be a semi-group. Here that property changed to the set with second operator should also be an abelian group. So here is the question. Here we will check this set for both ring and field. So here Z plus, the set is Z plus is 0, 1, 2, 3, 4. So this is the set. This is addition modulo 5 and this is multiplication modulo 5. So here we will check for all the properties. The first property is Z5. I will check for ring or I will check for field. The properties of ring will be checked in between. Z5 with addition modulo 5 should be an abelian group. Z5 with multiplication modulo 5 should be an abelian group. And Z5 and the last property is distributive property. So I will check for the first case. Z5 with addition modulo 5. So I will check the first case is algebraic structure, whether this is a algebraic structure or not. So for algebraic structure, this structure should satisfy closure property. So to check whether this structure satisfies closure property, I have to draw the closure table. The operator is addition modulo 5. So this will be 0, 1, 2, 3. Here 1. The addition modulo 5 operator is also explained in the previous lectures of this unit. Kindly refer those lectures. 1 plus 1 is 2 and the remainder will be 2. This is 3, this is 4 and this will give you 0. 2 plus 0 is 2. This is 3, this is 4 and this will give 0, 1. Here 3, 4, 0, 1, 4, 0, 1, 2, 3. This closure property is satisfied as we are getting by performing addition modulo 5 between any two number, we are getting the number which belongs to this particular set Z5. So closure property is satisfied. Now we will check for associative property. Consider any three numbers. Let me consider 1, 2, 3. Let me consider 1, 2, 3. So if we change the operator, If we change the association between the operator, the result will not be changed. 2 plus 1, it is 3. Addition modulo 3, it will give us 1. Here 1 addition modulo 5, this will give us 0. So here it is 1. So associative property is satisfied. So it is a semigroup. Next step, third property is identity. So here identity element for addition is always 0 and 0 belongs to Z5. So identity element exists. Fourth property is inverse. We will check for inverse. Inverse of 0 is identity element. By performing 0 addition modulo 5 between two zeros, we will get the identity element. So 0 is the inverse of 0. The inverse of 1 is 4. Inverse of 2 is 3. Inverse of 3 is 2. Inverse of 4 is 1. So inverse of each of the element exists. It is also satisfied. The fourth property is commutative property. We can check for commutative property. Consider any two numbers from this set and we will check for commutation. So it is 3 is equal to 3. So commutative property is also satisfied. So Z5 is a abelian group. Now we will check for Z5 with multiplication modulo 5. So we have to draw the Similarly, we have to draw the closure table for multiplication modulo 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So it is 0, 1, 2, sorry, 0. 0 into 0 is always 0. 1 into 0 is 0. 1 into 1, 1. 1, 2 is 2. 1, 3 is 3. This is 4. 2 zeros are 0. 2, 1 is 2. 2, 2 is 4. 3, 2, 6 will give remainder 1. 4, 2, 8 will give remainder 3. 3, 0, 0, 3, 1, 3, 3, 2, 6, which will give remainder 1. 3, 3, 9. When we will divide 9 by 5, we will get remainder 4. 3, 4, 12. And we will divide it by 5, we will get remainder 2. 4 into 0 is 0. 4 into 1 is 4. 4 into 2 is 8. When we divide it by 5, we will get remainder 3. 4. Now we will get remainder A and now it is 1. So from this table, we can see that the closure property is satisfied. Now we will check for associative properties, semigroup or not. Consider any two element. This is multiplication modulo. Sorry, this is multiplication modulo 5. So consider any three elements and change the association. We will check for associative property. Will it satisfy or not? 2 1 is 2, we will get 2 as the remainder. Multiplication modulo 5, 3. Here 1 multiplication modulo 5 and 3 2 is 6, we will get 1 as remainder. So we will get 1 as remainder. Here 1 into 1 is 1, we will get 1 as remainder. So associative property is also satisfied. So here it is first property closure satisfied, second associative satisfied. So this is a semigroup. Now we will check for identity element. So for multiplication, we know that identity element is 1 and we know that 1 is here in this group. So identity element exists. Now we will check for fourth property, which is inverse. So here we will check for inverse. So for 1, here identity element is 1. So the inverse of 1 is 1. Inverse of 2 is 3. Inverse of 3 is 2. Inverse of 4 is 4. But inverse of 0 does not exist. So this is not a group. The fourth property is not satisfying. When it is not a group, it cannot be a abelian group. So this is a semigroup, but not the abelian group. Now we will check for the third property, distributive property. Here I will check for the third property. Consider any three element. 1 multiplication modulo. This is, you can take anything. 1 multiplication modulo 5 and 2 addition modulo 5, 3. Will it be equal to 1 multiplication modulo 5, 2 plus 1 multiplication modulo 5, 3. So here I will check 1 multiplication modulo 5, here 3, 2, it will give us 0. So inverse will be, remainder will be 0. So 1 into 0 is, this will give us 0. LHS will be 0 here. 2 into 1 will give us 2 and it will give us, this is addition modulo 5, it will also give us 0. So here distributive property is satisfied. So the first property is satisfied, last property is satisfied, and the second property, it is not the abelian group, but it is a semi group. So this is a ring but not a field. These are the references. Thank you for patience listening. Thank you so much.